Hello, today we will be talking about the approximate analytical methods. We will use these methods to solve the differential equations that we derived before. The first one that I want to talk about is the Castilianos Theorem. So let's take a system, a simple system. Let's say that we have a spring here and I apply a force in the downward direction. And the spring has a stiffness K. So when I apply a force, I'll see a deformation, let's call it U, and I'll see the same deformation here. Okay, so the strain energy of the system is as follows. U is equal to 1/2. The force is K times U multiplied by the displacement. And the external work is the work done by the force. Okay, so the total potential energy can be written as follows. Pi is equal to 1/2 K times U square minus P times U. Okay, so let's call this equation 1. So since we have the total potential energy equation of the system, we can say the following. In order to be in equilibrium, the system must have the minimum potential energy. And we can just write it in equation form as follows. Del P over del U is equal to 0. So if I take the first derivative of the above equation, so del P over del U, it will become equal to K times U minus P equal to 0. So from that equation, I obtain P as equal to K times U. Right? So from that you can solve for U, and if you think about it, that's our equilibrium equation. So that sounds like a very simple approach, but the problem with this method is you have to calculate the external work. I mean, we can calculate the internal work for it in terms of U, but what about the external work? Now I'll give you an example. Now let's say that I have a simply supported beam. How do you calculate the external work of a uniformly distributed load? Because we don't know the variation of U, right? And we cannot calculate the external work. That's the main limitation. If you have a point load, you determine the displacement under the point load and then write down your external work. But if you have a more complicated loading, more complicated deformations in a system, then using this method becomes very difficult. So that's why we have the virtual displacement method. And in that method is I apply a virtual displacement, not an actual displacement, but a virtual one. And I can actually determine the displaced shape the way I want, provided that it satisfies the boundary conditions. And at the end of the day, even if with this virtual displacement, even if it doesn't match the exact displacement, I will get the solution. Okay, so let's take a look at it. Now I'll draw the same figure now. This is K. And from that K, I know that it will displace by U amount. So this is U. I don't know its value or the variation, but just show it. Okay, so this is the system. Let me show P here. This is the system, right? So what I'm going to do is I will apply a virtual displacement. The rule for applying the virtual displacement is it has to satisfy the boundary conditions. So I apply a virtual displacement like that, virtual, and the same displacement here. So the rule here is, of course, in that specific structure, whatever I have here, I should have the same displacement at the end, because that's satisfy the geometric boundary condition. So now what I did is we apply a virtual displacement that satisfies the geometric boundary conditions. Or we can just say that the essential boundary conditions. Okay, so since the displacement is virtual, is not really on the system, we can calculate the virtual work. So the work we calculate because of that displacement will not be the actual work, but it will be the virtual work. The virtual internal work. Let's show it with the symbol, is equal to internal force times the virtual displacement. So internal force is equal to K times U, and the virtual internal force is del U. Now let's calculate the virtual external work. It's basically force times the virtual displacement. Now what I'm going to write is the total potential energy functional. That's basically the virtual total potential energy. is equal to virtual internal work minus virtual external work. And that should be equal to 0. That's the stationary condition. And if I put these two equation into that one, I'll obtain again my equilibrium equation. So I have K times U minus P multiplied by the virtual displacement should be equal to 0. And again, if you think about it, that's the equilibrium equation. And since we know that this is not equal to 0, this condition must be satisfied. Right, but if you take a look at this, what I did here, it's very similar to what we were doing in the variational calculus, right? So let's do that also. I will just write the total potential energy of the whole system, which is equal to 1 over 2 K times U square minus P times U, right? So taking the first variation, so the variation in the total potential energy functional should be equal to K times U times the variation in the displacement minus P times the variation in the displacement. And we know that the stationary condition, the equilibrium condition, must say that this should be equal to 0. And of course, I get the same equation. So basically, what we are saying as the virtual displacement method is nothing but the variational approach. You have an energy equation, you take the first variation, and the first variation, if you give the variation to the displacement, the first variation will give you the equilibrium equation. What was the rule in the variational calculus related to the variations? It has to satisfy the essential boundary conditions. So that's again the rule. Whatever you give as a virtual displacement, you are free to choose any function. It has to satisfy the geometric boundary conditions. Okay, so let's work on an example now. So let's say that I have the following structure. This is L over 4. So it's actually divided into 4 pieces. So we apply P to the middle of the structure. Here, this is EI over 2. And that's EI. So the question here is, calculate the maximum displacement in this structure. So consider only bending deformation. Okay, so in order to solve this, I'll use an approximate function. So let's use third order polynomial function. So v is equal to a1 times x cubed plus a2 times x squared plus a3 times x plus a4. Okay. Now let's first use the things we know and simplify this equation. Let's use the boundary conditions now. I know that at x is equal to 0, the displacement should be equal to 0. So this tells me that a4 is equal to 0. At x is equal to 0, the rotation must be equal to 0, so dv over dx must be equal to 0, so this tells me that a3 is equal to 0. Okay. Now, I'm interested in the maximum displacement. So I know that that's a symmetrical structure, so I will see a deformed shape in this form, and I'm interested in calculating this displacement only, Vmax, and this displacement of course is under the applied point load. So with this approach, if I represent this equation in terms of Vmax, I can actually use the Castilianos Theorem also. Okay, so, and of course the other issue is, in order to write the energy equation, I have to represent everything in terms of the degrees of freedoms or the displacement quantities. Okay, so let's use the symmetry information. So I have a symmetric structure. So at x is equal to L over 2, v is equal to Vmax, and from there I obtain Vmax as equal to a1 times L cubed over 8 plus a2 times L squared over 4. And also at x is equal to L over 2, I know that dv over dx is equal to 0, and from that equation I have 3 over 4 a1 times L squared plus a2 times L is equal to 0, and this tells me that a2 is equal to minus 3 over 4 a1 L squared, and combining these two equations I can write my polynomial function as follows. V is equal to minus 16x cubed divided by L cubed plus 12x squared divided by L squared V max. Okay, so at the end of the day, that's the polynomial equation, that's my trial function, and my trial function is written in terms of the middle displacement. So this has a meaning, right? It's a displacement, and since and I can calculate the energy of the system. So let's write the internal strain energy expression. So U is equal to integral 1/2 the force for the bending deformation, which is the moment, multiplied by the curvature. Curvature is m/ei, and I have to integrate it over the length of the member. And we know that this expression is equal to d square v divided by dx squared. Okay, so the second derivative of this trial function is, let's calculate that, d square v dx squared is equal to minus 24 divided by L squared 1 minus 4x over L multiplied by the Vmax. Put it into the strain energy equation. So U is equal to, I have two sides, so I have to multiply the energy by 2, right? I divide the structure from the middle and just write the equations for the left hand side. So the total potential energy I have to multiply it with 2. I'm integrating it from 0 to L/2 in that case. 1/2. So EI times d square v divided by dx squared times dx. So in that equation I just represent the moment also as EI times the curvature. Okay, so we integrate that in two pieces. Here from 0 to L/4 I have EI/2. From L/4 to L/2 I have EI. And you do all these calculations, and at the end of the day we obtain U as equal to 72 EI over L cubed Vmax squared. Okay, so that's the internal strain energy. So the external energy is very straightforward, because that's P, and my variable in this trial function is Vmax. I have only one variable, so P will be equal to P times Vmax. Sorry, I said V, but this should be W. Okay, so as a first solution case, let's use the Castilianos theorem. Because we have the same variable in both at U and W. So we have the total potential energy. Let's write the total potential energy. U minus W. So I'm taking derivative of P with respect to Vmax, that's my variable. So I have del U over del Vmax minus P equal to 0. And from that equation, I obtain P as del U over del Vmax. And when you calculate that, that's equal to 144 EI over L cubed Vmax. And I'm obtaining the maximum displacement in the structure as P times L cubed divided by 144 EI. So that's the approach with the Castilianos theorem. And since that's a very simple structure, we can easily calculate the external work. I could use the Castilianos theorem and obtain the maximum displacement. Now let's use the virtual displacement approach. So my total potential energy functional is equal to internal work Vmax squared minus P times Vmax. Okay, so I don't really worry about the forces and the work done by each force. So I'm just taking the first variation, we call it stationary principle. In other words, I'm taking the first variation of this energy functional. The first variation will be equal to 144 EIZ divided by L cubed Vmax multiplied by the virtual or the variation in the displacement minus P times variation in the displacement, and that should be equal to 0. And from that equation I obtain 0 as equal to 144 EI L cubed Vmax minus P variation in Vmax, and from that I obtain the same result, Vmax as equal to PL cubed over 144 EI. So in the virtual displacement method, you can define any trial function, any polynomial function, maybe a trigonometric function. The important thing is it has to satisfy the essential boundary conditions. So in that case, that will be these ones. And it should be written right in terms of the some degrees of freedom. So you can directly calculate the internal and external work. The Castilianos theorem is very limited because this part is very tricky, but with the virtual displacement you can just define any virtual function and write down the stationary principle directly. Now let's talk about the third approximate method. We call it Rayleigh-Ritz method. Now, as we said, it's an approximate solution. And it's based on the principle of virtual displacement. On the principle of virtual displacements. Now, in this approach, the displacements or the displacement field is approximated by the following function. So we have some undetermined parameters and the function of unknowns plus a constant. So in this equation, AI is the parameters that we will be determining. And this phi are the functions of positions. So we said that it's based on the principle of virtual displacements. In other words, based on the variations. So the functions that we have to use should obey some rules, right? They have to be continuous and admissible. So what do we understand from the admissible? They satisfy geometric or essential boundary conditions. So we can choose any function that we want, but in general, in this approach, we choose phi as a polynomial or a trigonometric function. Now we define a displacement field, and by using that displacement field, we write the total potential energy, functional. Again, we are using the energy approach. And applying stationary principle, we have the following is equal to I is equal to 1 to n. That P over that AI, and the variation in AI must be equal to 0. And from that expression, we know that P over that AI must be equal to 0, and I changes from 1 to n. Okay, so the main difference of this method from the other approximate methods, these AIs, these undetermined parameters, doesn't need to have any physical meaning, or doesn't have to be any degrees of freedoms in the system. It can be any parameter. Even though they don't have a physical meaning, they can still provide us the results that we are looking for. Okay, so that's the main difference of this method from the other approximate methods. Okay, so let's put some notes here as general observations. So here the AI, these constants, can either be a set of coefficients with no physical meaning, or they can be variables associated with nodal displacements. So if the coordinates or this phi function satisfy the aforementioned properties, that is, they have to be continuous, they have to be admissible, solution converges to the exact as number of variables increase. Because if we add more variables, more a to this function, it will increase the accuracy of the solution. All right? And final observation. Now the equilibrium equations are satisfied only in the energy sense. And not in differential sense. Right? We know that we are actually doing a weak solution, weak form solution. Okay? So you can satisfy the energy, but don't expect that the equilibrium is satisfied at every point in this structure. Therefore, the displacements obtained from this approximation let's not say do not, but let's say may not satisfy equilibrium equations. Okay, now let's work on again an example problem. This time I'm taking a simply supported beam under uniformly distributed load. And length is L. Okay, so my approximate function, so I'm approximating the vertical displacement V, so that will be the V as a polynomial function. So I have A1 x L minus x. The reason of writing this as follows is, as x is equal to 0, v is equal to 0, at x is equal to L, v is equal to L. Okay, so this one satisfies the essential boundary conditions, and also it's a continuous function. So we satisfy all the requirements of a trial function. And this can continue. A2 is equal to x squared L minus x squared, and you can increase the parameters. Okay, so for this case, let's use the simplest version. So I'll say for this solution, let's use V is equal to the first one, just A1 x times L minus x. That's our trial function. And we said it, but let's write it down. At x is equal to 0, v is equal to 0, and at x is equal to L, v is equal to 0. So that's correct. It satisfies the essential boundary conditions, and that's all we need for the approximate solution. Now what we need to do is to, is to write down the boundary conditions, the energy function. So U is equal to, from 0 to L, 1 over 2 m times m over EI dx, right? Force, displacement, force corresponding deformation, multiply that 1 over 2, integrate over the whole area, you get your internal energy. That's equal to 1 over 2 from 0 to L. So m is equal to EI times curvature. M over EI is already a curvature, so I got EI d square V divided by dx squared dx, and put V into that equation. We will get from 0 to L EI over 2, and I have minus 2 A1 squared dx, and that's equal to EI over 2 4 times A1 squared L. Let's further simplify it, 2 A1 squared EI L, and that's the internal energy. Now the external energy, it's the work done by the uniformly distributed load. So again, I have to integrate it. V is constant with respect to length, multiplied by W is constant, V is Vx times dx, and when you evaluate that, we have dx as equal to A1 W L cubed over 2 minus A1 W L cubed over 3. And if we simplify that, this is equal to A1 times W L cubed over 6. So our total potential energy functional will be equal to 2 times A1 squared EI times L minus A1 W L cubed over 6. Now if we just take the derivative with respect to A, del P over del A1 will give me 4 times A1 EI multiplied by L minus WL cubed over 6. And from that I obtained the coefficient A1 as equal to WL squared divided by 24 EI. Okay, so as you see, we get the value of A1, but really what is the physical meaning? We don't really care actually. We just put it into the displacement interpolation, the displacement field, and that will become equal to W L to the power 4 24 EI x over L minus x squared divided by L squared is the displacement function. Okay, so if we want to calculate the displacement of x at the middle of the structure, we get the maximum displacement, which is equal to W L to the power 4 96 EI. But we know that the exact value of this maximum displacement when you do a differential solution is 5W L to the power 4 divided by 384, and we got 17% error. But of course, if you use a higher order, if you just add this variable and determine the values of A1 and A2, you get a better displacement field approximation and you get a smaller error. The important thing here is, as you see, these coefficients, the A1, A2, or you can use more coefficients, doesn't have a physical meaning, but at the end of the day, it helped us to determine the displacement field interpolation.